There we go. All right, here we go. Um, Ray 1, we always draw, you can see from the object parallel to the principal axis. So straight into the mirror, and then it reflects through the focal point, right? So you can see the ray going straight in and reflecting through the focal point. Ray 2, we go from the object through the focal point, and then it reflects parallel to the principal axis. It reflects straight out. And where those two things intersect, those two reflected lines intersect, that is where the image appears. Okay, so that's where I held the screen, right? I held the piece of paper yesterday, and we saw the flame on there, right? That's the point there that the image is at. Okay, ray 3, if you want to draw a third line, it goes from the object through that line that goes object and center point, and it comes straight back. And again, you can see now all three lines intersect at the same point. I never draw ray 3. You don't really need it, but I never, but it is a third ray that you could choose to draw if you wanted. Okay, so let us continue. Why is this not sliding? Go to the next slide. All right, and so we have a couple of things. So I hit share. Did it share? It did not. So let me stop sharing and then share a different screen for the hyperlink. Share. Right, concave mirrors, ray diagrams. Right, again, this is just kind of the same thing what we just did, the steps, but there is a little animation that goes along with it. And that's what I wanted to show. I didn't get to it. Let's do it. Right, so there's your two rays. Right, this again, it only draws two things, right? You can see one's going parallel and then reflects through the focal point. The other one goes through the focal point and reflects back parallel, right? Notice that the image is inverted, right? It's upside down in this case. The image is inverted, right? And depending on where you put the object, and when we get to the next hyperlink and the next thing I'm going to show you, maybe I can do that right now. Lenses and mirrors. Are you seeing this? Lenses and mirrors? Yes? No? Okay, good. All right, depending on this time, I want to go to mirrors here. Depending on where I put the object, right? My object, this is the object. The candle here is the object. It moves the image, right? But the image is always inverted, right? So this is a real image because it is in front of the mirror. The light's actually there. Okay, so that makes it a real image. And you can see that the further away the object is with a concave mirror, the further away the object is, the smaller the image gets, and the closer to the mirror the image is. And as I move it closer, the center point, 2F, is the center point, center radius of the curve, of the circle. You get the exact same thing. And as I move it closer to the focal point, the image gets bigger and further away from the mirror, right? One of the things that we're going to get to is, as we finish up the slides here on mirrors, is magnification also. So magnification is obviously how much bigger or smaller the image is compared to the object. Now, the weird thing about concave images or concave mirrors is if I move the object inside the focal point, the image now all of a sudden, right? First of all, when I move it on the focal point, if it's on the focal point, notice that the reflection rays are parallel to each other. So it says that there's an image way out in space to the right. But in reality, when the object's on the focal point, there is no image because those reflection rays never cross each other. So there's no place that they can all meet. So there is no image when, or it's an infinite distance away is actually probably a better way to put it. It's an infinite distance away, and therefore, effectively, there's no image. But when we move the object inside the focal point, now you can see the rays are going to intersect, but they're going to intersect out here to the right of the mirror, right? The right of the mirror, they're on a way to if I move it closer, there it is. And there's your image. This is a virtual image, right? I can't, if I put the object inside the focal point where the light actually is, out here on the left side, where the light actually is, never converges together, right? So there's no intersection of the reflected rays, so there's no real image. The reflected rays converge and intersect behind the mirror. There's no actual light behind the mirror, so that is a virtual image, right? But the rules of how to draw the ray diagram are still the same, right? This one has all three in it, but again, the first ray goes straight into the mirror and reflects through the focal point. The second ray is this one, actually, right? It goes through the focal point to the mirror and reflects back. I don't know why it's drawn this way, right? Here and reflects back parallel. And where they intersect is where the image appears, right? This is a third ray, which just kind of goes through the middle of the mirror. So, right, you can't. Yes. So if you're looking in this mirror, when you look at, right, when you look in the, it exists, you can see in the mirror, right? When you look in the mirror at this thing, you're going to see a candle in this case, but it's going to be bigger. It's going to be magnified, right? It's going to be bigger than the actual candle, and it's going to be upright. Whereas when the candle, we place it outside the focal point, when you look in the mirror, you're going to see a inverted candle, and whether it's magnified or smaller, it depends on where we put the object. But that's what this is what you're going to see, right? The image is what you're going to see, and whether it's real or not is based on where the light is, where all those rays, right? And whether we can put it on a screen. But you don't have to put it on a screen in order to see it, right? But if you can put it on a screen somewhere, right? So this is, and that's always kind of a confusing thing. The image, you're going to see something. You're going to see the image yourself, whether it's real or not, right? The definition of real means the light can converge, and if it's an imaginary or it's a virtual image, the light can't actually converge. Okay. All right, so those are array diagram stuff. Convex mirrors, I'm going to stop sharing. Convex mirrors essentially are the same thing, except you can see kind of in the ray diagram, the convex mirrors, the object is in front of the mirror, right? The mirror surface of the mirror is on the outside of the curve. So curve ray 1 goes in and reflects, but the focal point is behind the mirror because of the shape of the circle, the shape of the arc of the mirror. So it has this imaginary line ray, reflection ray through the focal point. Oh, did I forget to? I forgot to share it. I apologize. I stopped sharing something before and then I forgot to share the, where's Zoom? Share the, I went back to the PowerPoint and I forgot to start sharing the PowerPoint again. I apologize. Right? So this is a convex mirror. Right? Again, here's the three rays. I always only draw rays 1 and 2. Ray 1 towards the mirror, reflects off and then through the focal point, but it's imaginary behind the mirror. Ray 2 is not drawn on here. Ray 2 goes through the focal point, right? Through the focal point. For some reason they didn't put Ray 2 on I couldn't find this picture that had Ray 2 on there. Goes through the focal point and then reflects straight out parallel to the principal axis. So if you could imagine a dashed line, it would meet at the, whoops, it would meet at the object. Shit, I screwed up again. I mean, shucks. Don't want to offend anyone by using profane language, right? And the image, you can see where all those virtual reflection lines meet are behind the mirror. So for a convex mirror, you always end up with a upright imaginary image or upright virtual image, right? This is, we said before, right, that when you're driving, the passenger side, it says objects are closer than they appear, because when you look at it, you will see if this is, you're right, the object is the truck that's in the other lane. But when you look and see it in the mirror, the image you see in the mirror is smaller. And small things in our brain mean they're further away. Right? So when you look in the mirror, you're going to see that image of the truck, that virtual image of the truck or the car in the other lane, and it's going to look smaller than it actually is, which means your brain is going to say, oh, that thing's pretty far back, but it's not. So those mirrors are convex mirrors, right? You guys are too young to remember this. I don't even know if they even existed because now everyone has security cameras in stores. The round mirrors in the corners of the stores, are they still there? In like 7-Eleven and Wawa and those kind of stuff? Walgreens? The round, they're convex mirrors because the shape of them allows you to, the things that end up getting reflected to your eye, they all appear small, but it gives, because of the curve of the mirror, you can see more of the store. Yes. Right? So you can see more of the store, but so they use convex mirrors that way, right? So now we have security cameras in addition to these mirrors. But it used to be the security measure. You could look up and see if anyone is stealing, in theory. right? And shoplifters and all those bad people like you, Dylan, right? I can see in your eye you're a shoplifter. No? Okay. All right. There is a hyperlink for this one, so I'm gonna have to stop. Let me open the hyperlink first. I'm gonna stop sharing because you can't see the hyperlink. And go to that. Here we go, right? And I got it right now, ray diagram, convex mirrors. You're seeing? Good. And then somewhere down here, there should be a I guess I thought there was another like thing. Where was it? Where was it? They're all the same thing. Ray diagrams for here. Is this it? There it is. For concave, I don't want concave. We did concave. Come on. Okay. I guess it's not, there isn't a simulation of it, but you can see, right, those are our rays. The first ray goes straight into the convex mirror, and then it reflects. It's going to reflect away from the focal point, and we have that dashed imaginary virtual ray behind the mirror, and then the second one goes towards the focal point, and it reflects parallel to the, right, reflects parallel to the thing, and you can imagine those two red rays go back, and there's your image. Okay. I thought there was a simulation on this, but apparently I am wrong. I thought that's why I put it in there. Clearly I am an idiot. Oh well. Okay, let's finish up here. Back to my PowerPoint. Okay, last thing. Oh, I have to share. I forgot to share the PowerPoint again. Let me go back. Zoom, share, PowerPoint. One last slide. Okay, one last slide. Two equations for optics with mirrors, right? The mirror equation is 1 over the object, right, distance, plus 1 over the image distance is equal to 1 over the focal point, the focal distance. Positives and negatives, sign convention matters here, right? Anything that is on the reflective side in front of the mirror is positive. Anything that is behind the mirror is negative. So concave mirrors, the focal point is always, well, for every mirror, the object's always in front of the mirror. So the object's always positive, right? The distance of the object is always positive. For concave mirrors, the focal point is in front of the mirror. Therefore, the focal distance is always positive. The image distance varies. We saw it could be positive or negative because we saw we had real images or imaginary virtual images. For convex mirrors, we just saw, again, object is always positive because it's always in front of the mirror. For a convex mirror, the focal point, the focal distance will always be negative because it's behind the mirror. And the image distance will always be negative because that's always going to be behind the mirror also, right? The magnification formulas there are given to you. On your formula sheet, the magnifications are all absolute value, okay? If you end up, right, you can see you could potentially have a negative magnification. That just tells you it's inverted, right? But on your formula sheet, it's written in absolute values. So on any FRQ or anything. They're not going to ask you, unless they ask you to draw a ray diagram, they're not going to ask you if it's inverted or not, because they're only going to ask for the absolute value of the magnification. Okay, but if you would get a negative magnification here, you could get, it would just mean that's an inverted image, right? And the heights, again, you could get negative because the object height is always positive, but if it's inverted, you would measure your image height as a negative, so you get a negative over a positive. That's why they don't put the negative into that formula there on the slide. Good. All right, guys, I ate up. What time is it? We were supposed to be here till 11:59. It is now 11:57. Excellent. Stop sharing. Stop recording.